Hey, welcome everyone to the When to Be Weird session by Michael. We're glad Michael can join us today. So without further delay, over to you, Michael.
Cool, thank you. Here, give me one sec. Let me get the slide shared. All right, very good. So everyone, good morning for me. I think it's good morning for most people right now. Welcome to the talk. I'm going to be talking today about something I call when to be weird. So the first question is, what exactly do I mean by weird? I probably should have looked this up before before deciding on the title of the talk. But I decided, you know what, let's go look at the dictionary definition. And I like that first definition. We're going to go with that. Of strange, extraordinary character. Odd, fantastic. What we're going to be talking about today is when you're writing software. When does it make sense to be extraordinary, to be odd, to be fantastic, versus being ordinary, normal? You may notice there are some other definitions of weird, such as witchcraft, soothsayer. Those are somewhat related as well, but we're not really going to get into those today. So let me give an example of being weird. If you're not sure, this is an AI-generated version of lemmings. Lemmings are creatures that just follow each other off a cliff and all die. I don't actually know how true that is in practice, but that's the thing they're known for. If you see a bunch of people jumping off a cliff, you should probably not do it also. Do your own thing and ignore what everyone else is doing. However, and now we'll go to slide 4, there are some exceptions to that rule. Sometimes the general populace has everything right. For those who aren't seen it, this is the Flat Earth Society. So with flat earthers, they also think that everyone else has it wrong. They just happen to be wrong about it. So it can't be as simple as just be weird at all times. Let me give another example. We have a picture of a Ford Model T. This was a brand new kind of car that Henry Ford created. And he has a very famous quote about this, where he said, if I'd listened to customers, I'd have given them a faster horse. So disruption can be weird. Sometimes you can go ahead and you can change the way an entire industry works, and it actually turns out better. And sometimes you can come up with something like a segue, and you think you are going to revolutionize the world, but in practice, nothing good ends up coming from it at all. One more silly example, next slide, please. If you're an investor, you are looking for the next stock, the next asset, whatever it is you're looking to do, you want to be the early adopter. You want to get in first. You want to be weird. You want to get out there, and then you're going to get in before the big boom, and you're going to get rich. That's your goal. And by contrast, and you can see the chart showing lines going up. And by contrast, on the next slide, you can actually see the opposite. Sometimes you think what you're doing is actually the good kind of weird. Everyone else is selling off. You keep buying up, but it turns out that that inevitable pump that was going to come next just doesn't happen. So these are 3 little examples and that we're going to be using as a basis to understand. The question is, why do we care about any of this stuff at all? Maybe we should just build good software. Well, one thing is we as developers want the industry to improve. We want the technology to improve. We want the developer experience to get better over time. Understanding how these decisions make sense and how new things sometimes do and sometimes don't get adopted is core. Another thing we care about, the world regularly makes terrible tech decisions, and it would be really nice to at the very least understand why. Maybe we're not going to be able to do anything about it, but at the very least, it'll make us feel a little bit better if we understand why it's happening. We can also begin to predict the direction of our industry, which could be very useful for making job decisions, career path decisions for ourselves. And if we're very ambitious, if we understand the way that these things are decided by many people, we can actually begin to have an impact on the future shape of the industry. Next slide, please. I want to give some examples of weird things that actually won. One example of this is structured code. Many of us are not old enough to remember this, but back in the day, everything was done in assembly or BASIC or something like that with go-tos, jumps, all these various kinds of basic approaches, as opposed to control, if statements, while statements. We in the functional programming world sometimes look at if and while and for and say those should be statements, those should be expressions and other comments along those lines. But the point is, it used to be so much worse. We started off with something very simple and we went ahead and somebody at some point in time said, you know what, we can do better than that. And that's how we got structured code. Another example of a weird thing that worked was COBOL and the human language approach. If anyone's ever looked at COBOL code, you'll notice that it kind of looks like it's screaming at you at all times. At some point in our industry, there was a general consensus, or at least enough people believed this was going to be a successful approach going forward. Thankfully, it actually didn't win because it turned out to not be a great approach, but we can see that weird things can win even if they're not objectively good. We have an example, map reduce versus for loops galore. Many of us, when we got started with functional programming, trying to explain to someone why we wouldn't just want to use a for loop for every single bit of code that we were writing was very difficult. These days, it's become common practice. If you have a language like JavaScript, many people prefer using the more functional kind of approaches. The map reduce concept that came out from Google many years ago really made a difference in industry, and people began to understand, you know what, being weird about this can actually make our software better. Another example, there's this weird feature in Microsoft Internet Explorer many years ago called XML HTTP requests that was basically almost never used. And that eventually turned into AJAX and DHTML, and essentially what we have as the modern web. Whether we like that or not, it definitely changed the industry. Object-oriented coding is another example, encapsulation. All of these things were things that were introduced into industry, didn't start off as being the core way people do things, and for some reason did achieve adoption. Let's go on to the next slide. When we're talking about all of these things that could be introduced, what we're really talking about is a competition of ideas. And I'm going to use, once again, economic terms, because anyone who knows me knows I love using economic terms. So we're going to be talking about things like costs and benefits. Now, one of the things that often comes along in economics is we make some kind of an assumption about perfect knowledge and rational actors. We will get a little bit into that, but overall, my point is developers, for the most part, do not have perfect knowledge. I don't know at the beginning of a project whether path A or path B is going to work out better. So I need to make some kind of educated guess. And we also make some assumptions about rational actors. And one of the things worth mentioning, a lot of developers do not make their decisions based off of rational criteria. We do it based off of irrational criteria, the kinds of things that we enjoy writing code for. So it's something worth keeping in mind. So let's talk about, on the left side of the screen, I have this table, very simple, straightforward, costs and benefits. Costs are what we have to pay, benefits are what we receive in exchange. And we essentially get this 2x2 grid of 4 options. In practice, these are not binaries. We're not talking about something as either low cost or high cost. In practice, it's a spectrum. Some things are higher cost, some things are lower cost. But for simplicity, we're just talking about it in a binary approach. If you look in the bottom left of that chart, you have low cost and high benefit. If you're ever on a project where you think you can introduce something, and it's not the way you normally do things, but it has a very low cost and it's going to massively improve the project, that's the thing you want to focus on. You will get away with it. Your boss will almost certainly say, yes, go do that. When you have your boss tell you, yeah, I love that idea, it's usually because you found something like this. By contrast, you could have something that's low cost and low benefit. In that case, it's not difficult to make the pitch to be able to do it. And it's very easy to convince your manager, the project manager, the scrum master, whoever it is, hey, why don't we just go ahead and add this to the current sprint? And you can usually get away with it. The things that are much harder to talk about are the high costs. When we start talking about something which is high cost and high benefit, the concern there is risk, uncertainty about the future. Is this actually going to work out correctly? Or are we going to have some kind of problem with the integration? Were the estimates of the benefits incorrect? And then the worst of all is the high cost, low benefit. If you're not able to make a convincing argument why something is going to be massively helpful, and it's going to cost a lot to get it done, then you're going to just have a failure on your hands. Those are not the things that end up working out. So let's go on to the next slide. So since we are at a functional programming conference, obviously one of the things that we're going to talk about is functional programming. In fact, the rest of the talk, I promise you, we are going to see some code very shortly. So is functional programming the good kind of weird or the bad kind of weird? I would argue overall, functional programming is the good kind. We've introduced a lot of great things that have made the industry a better place. But I also think that it's a bad question because there really isn't something called FP. Yes, we talk about functional programming a lot, but the flavors of functional programming are vastly different. Some of the things within the functional programming space, through the rest of the talk, I'm going to argue are very good, and some of them are not as good. Let's see. Yeah, let's move on to the next slide. What are some of the patterns so that we can then begin to analyze individual features of functional programming? Things that succeed tend to be things that do not require rewriting the world. We'll see some really, I'll give a hint. Docker versus Nix is one of the big examples of that. Things that provide large benefits. Those are the things that get people's attention and will catch on. Small costs, if you can easily add it in, that's also something that's going to have some kind of an impact. I put this in quotes, sexiness. Things that look cool, that sound good, that you could go to investors and say, we're doing something cool. AI fits into this space. Sexiness tends to succeed as well, and things which are easier to work with. And if you're familiar with the phrase, the worse is better kind of approach applies here. Sometimes even if something is a great idea, if it is hard, if it's complicated, if it scares developers, it ends up failing even though it was a great idea. Now, by contrast, let's talk about some things that don't succeed. Correctness is one of those examples, and I'm sure someone out there is getting upset already. I'm actually upset about this myself, but I'm just telling you guys what I've seen as a pattern in industry. If you're able to come forward and say, hey, look, I came up with this great new approach, and it makes my code 27% more correct. People don't care very much. You have to have some kind of a really compelling use case, such as memory safety bugs account for 30% of all exploits in our code, and now we're going to get rid of all of those. Then you're able to really make the argument. But just an overall general, my code feels better, or I can reason about it better, those kinds of comments tend not to actually make much of a difference. And provides non-tangible benefits. You'll hear people say, yeah, but aesthetically pleasing or things like that. Those kinds of ideas definitely catch on with the developers, but the companies that are hiring them, that are paying for the products, are not going to care very much. Okay, so ultimately, my point is software is going to be judged, and it's going to be judged in a free market where the value of the software is not based off of these non-tangibles or the inners of how it's built. We need weird things. We need to find new approaches or leverage existing approaches that will actually have market value. So that was a lot of words. I promised code. We're going to see code next. And I'm going to give you some concrete examples. I'm going to give everyone the warning in advance because I'm sure I would be shocked if there's no one. I would assume everyone is going to walk away pretty upset by something I say today. I'm sharing my opinions. I am going to be very opinionated about it. I hope other people are opinionated about their opinions too on these things. My goal here is not to try to convince anyone that my opinion on each one of these features is correct. The goal is to share a thought process around how we make these judgment calls. So first section, victory lap, where we've already won. The first thing I want to talk about is typed programming. And basically my point with the next few sections, I don't think we're in weird territory anymore. Typed programming, maybe 20 years ago, it existed and it was considered pretty crappy. We had C++, we had Java. People, for the most part, really just hated typed programming. People loved Python and Perl and even PHP. It was a crazy time back in the day. And I would say that 20 years ago, typed programming was losing, and untyped programming or dynamically typed programming was the thing that was actually winning. Since then, we fought a valiant fight. Many people, myself included, I'm not saying I'm any leader, I'm just saying many people in the developer community have been fighting this fight, saying we actually think types are better. And at this point, I don't believe we're fighting a fight. I think we've won. What I mean by that is, even though some of the most popular languages on the planet today, like Python and JavaScript, still are dynamically typed languages, each one of these is actually being supplanted by some kind of a type system. Python has type annotations. Many people recommend using them on a regular basis. JavaScript, many people don't want to be using JavaScript at all. Everyone's moving over to TypeScript. Within the JVM and the .NET ecosystems, we see ideas from Scala and F# being massively embraced by industry. Rust is a language that's come out in the past 10 years, very strongly typed in its entire approach. I would say it takes a lot of ideas from FP, and Rust is gaining a lot of ground because of this. And I would say even Go, which I have to admit, I'm not any kind of a Go expert, even Go had to go ahead and add generics, which to some extent you could say is a non-typed programming. I understand Go was already a typed programming language, but it became more typed. Let's go to the next slide. So why did typed programming win? After all, it had lost previously based on the way that I presented things. First thing is, I think we had a huge improvement, which was type inference. Now, some people might say, well, that's not really such a big deal. People have used more complex type systems are already used to the idea that type inference is in fact a big deal. But even for simple cases like int x equals 5, it doesn't really, in fact, it's less characters to type int x than auto x or whatever it is that you're going to type in C++ these days. But nonetheless, people didn't want to have to do it. It added a cognitive overhead. You could argue it wasn't a very big cognitive overhead. Nonetheless, it was enough to add friction. And because of that, typed programming lost, or at least one piece of it. And once we got type inference to be a mainstay in most type programming languages, we began to win again. Another one was weak type systems. For people who aren't familiar with this, there's dynamic versus static, meaning do you check types at compile time? And then there's weak versus strong, which is how many guarantees can you put into the type system. A type system like C's doesn't actually have a lot of value in the types. You can distinguish between a character and an int, but even that doesn't really mean very much. Between a string and an int, but even they're still both ints under the surface. They're both pointers, or they can both be treated as pointers or ints. So as a result, you didn't get a lot of value and you were still paying the price in C. And here, I'm going to make the final point, I think, is the real reason why type inference has taken off, or sorry, why typed programming has taken off. And that is developer productivity. These days, LSP, the language server approach, is in everything. All of our different editors use it. We now have IntelliSense or autocomplete, and all of it works way better with types. And if I was really to take a guess, I think that's probably the primary reason. This had nothing to do with correctness of code, performance of code, or anything else. It came down to developers are lazy, and lazy in the best way possible. They want a nice, easy development experience. Let's go to the next slide. Sorry, my slides aren't moving. Here we go. So moving on from type, oh no, I went too far. There we go. So moving on from type programming, the next one is immutability by default. Not every this is actually going to get back to what I said before, that FP means so many things to so many people. But for me, immutability by default is really one of the core tenets of functional programming. And at this point, even though we have a whole bunch of languages out there that make immutability very difficult, it has still become the default for many programming recommendations in many languages. C and C++ have the insanity around consts that don't work particularly well. JavaScript has objects that always, to some extent, stay mutable, even if you put it inside React. You can see all of these difficulties you have with the languages. And despite the fact that the languages don't really provide first-class support for immutability, people still want to be doing things immutably. So this is one of those examples. You got huge benefits. It did require some kind of changes, but the changes turned out to not be as difficult for us to learn as many people would have thought in the first place. And that's the reason why I think immutability by default is winning. One of the really cool things about immutability is it doesn't just apply at the code level. You can also extend it to things like your DevOps or your infrastructure. Immutable infrastructure, approaches like infrastructure as code with Terraform, all of these kinds of things follow the same basic premises, and I don't think would have been as successful if we hadn't already won the battle on the programming side. Arguably also, I would say things like blockchain, getting content addressable storage all fit into this kind of this framework as well. All right, let's go to the next slide. So those were the easy ones. Now we're going to talk about places where I think we're winning the war, but we haven't actually completely won yet. Let's go on. Sum types. Anyone who's heard me talk about this at all has probably heard me praising sum types. If there's one single feature in functional programming languages that I think has the best power to weight ratio, meaning it gives a huge amount of benefit and costs very little to use, it's sum types. It's core to ML and Haskell. Rust uses it extensively. TypeScript uses it in slightly different way, but still uses it extensively. It destroys the need for some complicated design patterns like the visitor pattern. It is very easy to explain to people. I can basically say, hey, it's going to be X or Y. People already know about enumerations, enums. Teaching them that it's enums on steroids is great. And this all gives us very clear demonstrable benefits. We can do compiler-driven development. I've demonstrated to people many times in the past cases where you're able to add an additional data constructor variant to an enum. And suddenly the compiler is able to tell you every single line of code that needs to be updated to account for this new case. You have reduced bugs as a result of that. And sure, you could get a lot of those benefits by using the visitor pattern or doing something like church encoding. You could do it previously, but now the friction is much lower. The cost of using a sum type versus one of these more complicated approaches is much lower, and therefore people are more willing to do it. Let's see an example with some XML processing. At the top, we have the visitor pattern, and I'm using Java and SAX, which now I don't remember what SAX stands for, but it's the stream processing approach for XML in Java. And basically, the way this works is that there is a class, and you go ahead and you make a child class that implements each one of these methods. And the methods demonstrate how it is that you want to handle all the different cases. I started a new XML element, I ended an element, I got some characters, I got a processing instruction. There's a whole bunch of these different things. And sure, you could write code this way. I personally don't find it very convenient or palatable. And I think a lot of other people who have written code like that understand what I'm talking about. By contrast, on the bottom, you see the SAX processing equivalent in Haskell. Here, we have event. An event is a sum type, and it represents every single possible event that could happen when you're processing XML. And here, you can see we have the same concepts: begin an element, end an element, content, and so on. The thing about this is it becomes much easier to extend it. Now we're just dealing with normal data and normal functions. I don't have to go off and create an instance of some kind of interface. I don't have to create a child of an abstract class. I can simply write normal code the way I'd want to. I've written both versions of the code. Every day of the week, I would rather do the sum type version. Let's go to the next slide. So the question is, why haven't sum types fully won, given the fact that sum types are obviously great? The very simple reason is that many popular languages haven't embraced it yet. I think Java and C# are at a point in their evolution. It may be too late to add something as big as sum types. And then I'm very disappointed, but Go, when they launched, decided not to bother with sum types. We all know about how we all know about how error handling is done in Go. It's kind of inconvenient. Many programmers also are still unaware of sum types and of the value. The fact that this thing exists and is wonderful doesn't really do very much for programmers out there if they're not aware that they can use it or that they should be arguing to get them included in their programming languages. I also think the name itself sounds scary. I can't give you an explanation for why some names sound mathematical and scary and others don't. Parametric polymorphism sounds like a very scary name to me, and sum types doesn't. And yet, C++ developers, for the most part, feel exactly the opposite. So for whatever reason, sum types, I think, does scare people away a little bit just by names. And some people legitimately just fail to see the advantage of sum types. I've had people say, well, when would I ever want that? Overall, I haven't seen that to be a real issue most of the time. For the most part, most people understand that this is something valuable. Okay, next slide. So another thing that goes along very nicely with sum types is pattern matching. They don't have to be connected, but they often are. This is another one of those things that's very easy for programmers to understand, because you can basically say, you already know what a switch statement is. Now we're going to do more powerful switch statements. I'm going to go a little bit faster at this point because we're running out of time, so I'm going to keep moving. Auto-deriving is another one of these features that is language specific. In Haskell, we have deriving clauses. In Rust, we have the derive pragma. In Haskell, you can extend it with generics or with template Haskell or with other kinds of approaches. And in Rust, we have proc macros. Now, the advantage of both of these approaches, whether it's Haskell, Rust, or any other language that has this, we're able to remove boilerplate, make it easier to write code, make it easier to maintain code, and avoid bugs, which we're going to see on the next slide. I'm going to give everyone about 5-10 seconds. Look at the code and see if you can spot what the bug is. I'll look at the chat if anyone wants to type anything in. Missing case, very good. In the from stir case, you can see that we have red and blue handled, but we don't have green covered. It's relatively easy to see it in this case because all the code is sitting on one screen. Strangely enough, I reviewed a PR this week and missed the fact that someone introduced exactly this bug into a code base because we weren't using macros and we probably should have been. But let me go ahead and show you what this looks like if you use macros. Instead, we define our three cases, and then we simply let the macro do all of the deriving. It creates the from string, the to string, and now we have a guarantee that as long as the macro itself is correctly written, we have correct bidirectional parsing and rendering, meaning we never have to worry again about the possibility of missing one of our cases. All right, let's go on to the next section. This is the section, by the way, that's most likely to piss people off, which is great. All right, so great but niche, meaning these things don't provide as much value, though they are very cool. Software transactional memory, STM. Haskell has, I believe, one of the greatest features that has ever existed for shared memory concurrency. It is software transactional memory. It is easy to learn. It solves a real-world, well-understood problem, which is data races. The performance of it is really good. Sometimes it's even better than any alternative that you could come up with. But there is one massive catch with it. And the massive catch is STM doesn't work particularly well unless you have a pure programming language like Haskell. There have been attempts to put STM into other languages, hasn't gone particularly well. Let's go on to the next slide, green threads. Green threads are another one of those great ideas. It is the simplest way imaginable to write asynchronous I/O code because you don't have to think about it. You let the runtime handle everything. It completely solves what's become known as the function coloring problem. The fact that in languages like Rust and TypeScript, you have both the async and the non-async version of functions. In Haskell, in Go, and Erlang that have green threads, we don't have to worry about that. Instead, everything is just an asynchronous function. Green threads compose really nicely with whatever existing error handling exists. People who have dealt with JavaScript async or with Rust async back in the day understand that it's not so trivial always to be able to handle the error cases when you're dealing with futures. It avoids any need to litter our code with async await noise. So green threads seem like an obvious, easy win. The question is, why haven't they caught on? Why did I only list 3 languages that support them, though I'm sure there are others? Well, the catch is plenty of languages don't support them, so this thing can't catch on until they do. And many languages, Rust being a great example, have intentionally avoided green threads because they do actually introduce a problem. The problem they introduce is that it requires a runtime. A language like Rust simply can't support that. So as a result of these kinds of trade-offs, green threads, I think, are going to continue to be a niche thing. It is not going to end up dominating the entire industry. Let's move on. Macros, metaprogramming, code gen. I kind of touched on that previously with auto-deriving. I'm going to jump ahead and go to the next slide, and let's just go ahead and see a little bit of a code sample, and then I'm going to blitz through the rest of the slides because we're out of time. If you look at this code on the screen, this is how I do command line parsing in Rust. Instead of having to get down to low-level details, I'm able to define a high-level data structure that represents exactly what I want the user to be able to tell me, use pragmas, and with that, create a very nice-to-use command line interface together with help output, version output, all of these things coming out of the box. Doing them manually with any kind of another approach will always end up, at least in my experience, will always end up being much longer and harder to work with. JSON parsing with Cerity here. You can see that example. Just to blitz through the rest of the slides quickly, monads are one of those examples of a great idea that really does help code significantly. One more slide, please. The thing about monads is they are difficult to learn. They scare people away. And in many languages, they don't deliver the same value that we get out of the functional programming world, where monads were actually necessary to model problems. Nonetheless, I've actually had JavaScript developers not know that I was a Haskeller and say that Rust error handling was monadic because that's become the lingo that people are using. So to some extent, even if monads haven't taken over the world, to some extent, at least on the intellectual side, they seem to have. Next slide, another great example, type classes and traits. Any language that has introduced them, I think, has seen that they are great. They are better than interfaces. They're better than most other approaches for generalizing code. They're easy to understand. The only downside is the fact that you have to have them built into the language. And at this point, with many common object-oriented programming languages, we're simply not going to be able to add those back in at this point. Okay, so apparently we did not get to all of the controversial parts. I will let people look through that, and you can flame me on Twitter or anywhere, I guess X, flame me later on. Since I mentioned this one earlier on, I'll just mention briefly on the next slide, the Docker versus Nix versus unikernels. Nix and unikernels are examples of great ideas, things that people absolutely believe are a better way to do things. And yet Docker, which almost everyone thinks sucks, Docker is one, and people aren't going to like that. Why did Docker win when these other things failed? And this is, I guess, yeah, this is actually a great place to stop. They failed because Docker was the right kind of weird. It changed things just a little bit. Nix and unikernels required completely rethinking the way that you were going to approach building software, shipping software. Docker didn't. It had some changes to shipping software, but for the most part, it was you've got an image, which is your executable. You've got a script that's going to build things, and you use normal commands, and you're done. Are there problems with Docker? Absolutely. You do not get reproducible builds. You don't get all of the great benefits that you get with Nix, but you get 80% of the benefits with a fraction of the time. And that's the reason why Docker is one. And I think you're going to see, if you look through many other things coming from the functional programming world, the same logic applies. So with that, I'm going to call it here. And if anyone has any questions, we can go over to a Q&A.
Hey, I can see a couple of questions from Aaron here. So Aaron is asking, how much weirdness is a question of marketing versus actual benefit? There are often two ways to achieve something with arguably equivalent but different results.
Right. So you may have noticed the way that I presented this once again, because it's my shtick, was very much on the economic side. And on the economic side, the question is, how are we going to be successful? I can sit around and I can write code in my basement as long as I want. But if I'm not getting paid for it, I'm not really having some kind of an impact on industry. No one's actually stated, yes, I want you to be able to do things in the way that you have said is a better way to do things. So the question is, so does it come down to marketing versus actual benefits? It's not really either one of those. It's related to both. It's perceived shareholder value, if I had to put a term on it. If you can convince the management, the higher ups, the people who, the investors, the people who are funding projects, this is the right approach, then I think you're going to succeed. Now, you can succeed that way by having products that ship and make money for companies. You can do it in lots of ways that don't require proving technical competence, which is the reason why a language like COBOL, that at this point basically everyone hates, was able to be successful, because in practice they did deliver a lot of results for many, many years.
Got it. Another question from Aaron again. Do you think we have gone too far in trying to add new features? Is it time to remove intermediate innovations?
For the most part, yeah. But then again, it depends on the language that we're talking about. I think it's great to have lots of experimentation going on for experimentation's sake. The problem that I think has happened, and I've been guilty of pushing this myself, is, hey, I played with a great idea. It worked really nicely. Now it's time to push this directly into production. Many of the things that I thought were great ideas and I started using on commercial projects, they simply weren't ready to go. And maybe that's not such a bad big deal. Maybe the reality is this is the way features get tested, get shaken out. And maybe it is as simple as I'm older now, I'm more experienced now, and I'm more jaded now. And at this point, I think all you young people with all your cool ways of doing things, no, these things aren't necessary. I think I think this is probably just a normal kind of path through industry. Anything invented after you were 35 years old is too young, too new, and too stupid.
The next one is from Alexander. He's asking, so all these features won or lost, but what about FP in general?
So I gave a talk previously called FP is the new OOP, and that's going to be my answer here. I think FP is both won and lost. It won in the sense that the best ideas from functional programming, I believe, have taken over. My best example for that is Rust. You have a brand new language, and Rust, sure, it's not a functional programming language. No one claims it's a functional programming language, but it clearly was massively influenced by all of the FP ideas. We won. That wouldn't have happened 20 years ago. How do I know that? Because it didn't happen 20 years ago. We had languages coming out 20 years ago, and they weren't FP inspired. So at this point, I think the best ideas from functional programming have been stolen and adopted by other languages. And I say stolen with all love. They should be stolen, and I love it. The downside of this, though, is now functional programming is sitting around saying, hey, we have immutability, and everyone else says, so do we. Oh, we have some types, so do we. So what's left with functional programming? Well, a bunch of the controversial things that I didn't end up getting to, but things, sorry, someone's going to get upset. Category theory. Everyone is going to now point at functional programming and say, oh, that's the language you go to if you want to play around with arrows and Kleisli arrows and all those other weird things that don't make any sense. That's functional programming. Now, those of us who have been in the game for a while understand functional programming is much more than that. But I really think 10 years from now, that's all FP is going to be remembered for, while all of our great ideas are just considered programming.
Yep, that's a great answer. So that's all from the questions, and I think yeah, thank you, Michael, for this awesome session.
Thanks for everyone putting up with the technical difficulties today.
Yeah,
Really appreciate it.
thank you. Bye.
Bye.